So based on the notions of sets, we now define mappings. Let's say we have two sets, A and B. And let there be a rule or prescription, denoted by F. So for each element of A, there is assigned a unique element in B. So for this element, we assign this element. So this assignment is defined for every element in A. And this rule is called a mapping or map or function from A to B. And we write like this. Okay. For this, A is any element in this set. Okay, so that's mapping. And to indicate that F is a mapping on sets, we use this notation. So F colon A to B, or A to B and F is put here. Okay, and in this case, this is called domain, and this set is called codomain. Codomain. Okay, A is domain of F and B is the codomain of F. Okay, and this set, which is a subset of B, defined by, let's say, so the entire A is mapped into a subset of B, right? It does not necessarily cover entire B, but in general, this is a subset of B, and this is called defined by this. So for each element of A, there is an element in B. So the set of all such elements is a subset of B, and this is called the image of A. So this is called image of A. So this image of A by F, or we say this is the range of B, a range of F, range of F. Okay, and we write this as F of A. Okay, so this is a set. It's not a value. It's not an element of A, but it's an entire set. So this is just a notation of this set. And actually, we also write, let's see, let's say we have A and B. Let's pick a subset of A and pick each element of A and get the corresponding elements in B. So the entire set of these elements define a subset of B. Let's call this subset of A, let's say A prime. So A prime is a subset of A. We can write F of A prime. So this is a subset of B defined for each element of A prime. Okay. So this argument of f can be an element of A, in that case, which describes the mapping itself. And also, this argument can be a subset of A. In that case, it defines some subset of B. Okay? And when this subset of A happens to be the empty set, then we define its image as the empty set. Okay, let's see some examples. Let A be the set of 3 elements. So A, B, C. And let B be the set of 2 elements, 0 and 1. And we can define a mapping by this. So this is the definition. So A goes to 0, and B goes to 1, and C goes to 1. So this defines a mapping. And for this F, the domain is A. This is A. And the codomain is B. And the range is B, because B has only 2 elements, and the values of the function covers all elements in B. So the range or the image of A is B itself. Okay. And we can define another mapping. Let's say it's G. So for the same sets A and B, and G of A, in this case A, B, C, and 0, 1. So G of A is 1. So this is F, this is G, and G of B is 1. Sorry, it's 1. So G of A is 1, and G of B is 1, and G of C is 1. So every element of A are sent to 1 in B. So in this case, the domain is again A, the codomain is again B, of course, but the range in this case is the set of only one element, 1. Okay. We may say this F and this G are not equal, because this one, so F of A is 0, but G of A is 1. So their values, so their assignment of A, this element A, their assignments are different. So we can say this function G and function G and function F, they are different. That makes sense, I guess. But here's an exercise. So if F and G are mapping like this, give a definition of them being equal. So what does it mean that if two functions F and G are equal? What do you mean by this? Okay. So from this example, we can say they are not equal. But if they are equal, what does it mean? Okay. Okay. Now here's some notations. These notations are used very often in later chapters. So let's define this. And the natural numbers, The set of all natural numbers is denoted by this symbol. Okay, n. This is n. And I think you know what natural numbers are. It's 1, 2, 3, 4, 5, 6, and so on. And this n, of course, stands for natural. Okay, and the set of integers is denoted by z. So this comes from Zahl. It's a German word for number. And of course, integers are numbers like all the natural numbers plus 0 and negative of all natural numbers, like -1, -2, -3, and so on. Okay, this z represents the set of integers. And next, the set of rational numbers. I think you already know what rational numbers are, but here's a more or less formal definition. So it is actually a pair of two integers, m and n, where m can be any integers, but n can be integers that is not 0, okay, except for 0. So we write rational numbers like this. So this can be actually considered as a pair of integers. Okay. Now the set of real numbers. Oh, by the way, this is denoted by Q, which represents quotient. It's quotient. And the set of real numbers is denoted by R. We don't go into the details of what real numbers are, but I assume you somehow intuitively know what real numbers are. Okay, and the set of complex numbers is denoted by C.